Okay, let's continue with chemistry. Uh, with this particular slide here called hydrogen bonds. Um, we talked about covalent bonds, and there are really two types of covalent bonds, actually. Um, what's called non-polar covalent bond and or full covalent bond, and a polar covalent bond. And here's the so we have to bring in a very important concept, the concept of polarity, and that is in some uh, covalent bonds, particularly between um, two carbons, uh, that's called a full covalent, or between a carbon and a hydrogen is full covalent, and that in that kind of bond, what kind is it? In that kind of a bond, the electrons are shared equally, and so there's no charges associated with it. In a polar covalent bond, the electrons are not shared equally. They spend most of the time around one of the atoms, and since electrons are negatively charged, that side of the molecule becomes polar. It has a partial charge, and the atoms that really do this all the time is oxygen and nitrogen. They love electrons, and they try to take electrons away from the other atoms in the molecule. That makes it a polar molecule. So water is a polar molecule. It's H2O. So the oxygen tries to take the electrons away from the hydrogens, and sometimes it does, and it forms ions. Um, so the electrons spend more time around the oxygen, and they are negatively charged. So it gives the oxygen side of the water molecule a slight negative charge, and that means the hydrogen side of the uh, water molecule has a positive charge. So it's polar, like a magnet has two poles, a positive pole and negative pole. Um, and there's also if there's no oxygen or nitrogen in a molecule, it's called nonpolar. And there is segregation among molecules. Polar molecules mix with other polar molecules. Non-polar molecules mix with other non-polar molecules. And polar and non-polar don't mix. Best example is water and oil. Water is a polar molecule. Oil is a non-polar. You mix oil and water together, what happens? They layer out. They don't mix. Okay, the polarity of water results in weak electrical attractions called hydrogen bonds between neighboring water molecules. Now here's a bond that's between molecules, not within a molecule, but between molecules. But later on, we'll see that there's, when we get into macromolecules, we'll see that there are hydrogen bonds within those large molecules like proteins and nucleic acids. Okay, and these, here's an example of these hydrogen bonds. Every water molecule makes several bonds with nearby water molecules because, as I mentioned, the hydrogen side of the water molecule has a positive charge, the negative side has a negative charge, and remember, opposite charges attract. So the positive side of one molecule, water molecule, is attracted to the negative side of the other molecule. And these are really, really weak bonds. They're the weakest of all the bonds. Actually, we can grade the strength of bonds from strongest to weakest. Strongest is full covalent. That doesn't, they don't break apart. You really have to work out to break those bonds. Polar covalent are weaker. They sometimes come apart. And then ionic bonds are even weaker. They almost always fall apart in water. and hydrogen bonds are the weakest. But there are so many hydrogen bonds in even the smallest drop of water that it imparts uh, characteristics to water characteristics that are really important to life on Earth. And water behaves really sometimes bizarrely because of this ability to make hydrogen bonds. So this animation is not going to work. Okay. Um, when a lithium ion joins a bromide ion to form lithium bromide, the resulting bond is a what? Remember, lithium in column 1, bromine in column 7. Uh, bromine gives up an electron. Lithium gives up an electron to bromine because lithium bromide forms an ionic bond. Remember, columns 1 and 2 make ionic bonds with column 7. Okay. Cells constantly rearrange molecules. These called chemical reactions. Um, the reactants are the starting material, and they're on the left of the arrow. And then there's an arrow pointing to the products, the end materials. Remember, chemical reactions can rearrange matter but cannot create or destroy matter. They just rearrange it. And chemical reactions can require some energy to go forward. Sometimes there's very little energy, so they're called spontaneous reactions. Or sometimes they release energy. Okay, predict the formula for the compound that results from a molecule of sulfur trioxide, SO3. You're going to add H2O to SO3. So what's the resulting molecule going to be? Remember, you don't lose any atoms. So it has to be the oxygen and water is added to the O3 to make O4, and they got to add 2 hydrogens, so it's H2SO4. It happens to be sulfuric acid. Right. Cells constantly rearrange molecules by breaking existing chemical bonds and forming new ones. These are pathways that transform energy and matter. Life on Earth began in water and evolved there for 3 billion years before spreading out onto land. Modern life is still tied to water. Your cells are composed of 70 to 95% water. Water is what's called a biological solvent. We're going to get into solutions later on. We have at least two molecules mixed together where one is dissolved in the other. The one that does the dissolving is called a solvent, and the biological solvent for life on Earth is water. And the abundance of water is a major reason that Earth is habitable. As a matter of fact, when you want to look at other planets that might be harboring life, you got to look for a planet where you're going to have liquid water existing in that temperature zone called the habitable zone. Sometimes called the Goldilocks zone. Not too hot, not too cold, just right. And you got to have abundance of water. The polarity of water molecules and the hydrogen bonding that results explains most of water's life-supporting properties. We're going to get into those. Water world. 70% of the planet is covered by water. Okay, we know that water molecules stick together because of hydrogen bonding. So this gives water cohesion. And it's much stronger for water than for most other liquids. Trees depend on cohesion to help transport water from their roots to their leaves. Now we got a pump to pump fluids through our body. Trees don't have this, and they have to get water from the ground up to the leaves that could be hundreds of feet above the ground. So this is called capillarity. If you put a very tiny tubes in water, water will move up against gravity because of this cohesion. It's cohesive to it. It's cohesive to itself. As the water molecules move up the tube and attract it to the inside of the tube, which is called adhesion, then they pull up other water molecules with them. And this is there are several more forces that bring water up against gravity. this capillarity is one of them. Surface tension. How difficult is it to stretch or break the surface of liquid? Hydrogen bonds give water unusually high surface tension. You don't think it takes much to push the boundary between water and air, but if you get enough hydrogen bonds, you can float really, really heavy things in water. You can float aircraft carriers in water because of hydrogen bonds. Believe it or not, what's holding up the aircraft carrier are hydrogen bonds. Like I said, they're incredibly weak, but there's so many of them that they impart real strength to water. And it's called surface tension. Here's the, so just underneath the bark of trees are tiny little tubes called xylem tubes, and they help pull water up to the leaves. There's microscopic water conducting tubes. Cohesion by hydrogen bonding between water molecules brings water up the tree. It's called capillarity. Evaporation from the leaves also helps bring water up. Those are the xylem tubes, and that's the cohesion between water molecules. And here, this spider is able to walk on water. Why? Because the surface tension is holding up. See how each leg is dimpled a little bit. That's and in lab, what we usually have you do is float a pin. You can float a pin in water if you do it carefully enough. And it's hydrogen bonds that are holding up these things. Okay. Stronger resistance to temperature change. Heat is first used to break hydrogen bonds. Water absorption stores a large amount of heat while warming up only a few degrees. Water can hold on to heat. And this is one thing that is incredibly important to life on Earth, because during the day, the sun heats up the oceans and all large bodies of water, and that heat is stored. So when the sun goes down and our side of the Earth is turned away from the sun, it only goes down. Then this heat comes out of these big bodies of water, wafts over the land, and keeps the temperature between night and day pretty moderate. So like a few degrees, 10 degrees or something, 20 degrees. It would actually be hundreds of degrees probably if there wasn't any huge bodies of water on Earth. And then when water cools, it gives off heat. That's called evaporative cooling. When a substance evaporates and the surface of the liquid remains behind, cools down. So as water evaporates, it takes heat with it, and that's evaporative cooling, which we use when we work out in a hot environment. We sweat, and that sweat evaporates off and keeps us cool. We got a great cooling mechanism with evaporative cooling. And there's evaporative cooling right there. Okay, when molecules get cold enough, they move apart, forming ice. Here's a really bizarre thing with water. Most things, liquids particularly, when you cool them down, they get denser. And density is a measure of how far apart the molecules are. You know, the farther apart they are, the less dense. The closer they are, the more dense. So as you have like room temperature water and they start to cool it down, the water molecules get closer and closer and closer together. Just like every liquid, but something really strange happens at 4 degrees C. They stop coming closer together and they move farther apart. And then they form ice. And so ice is less dense than liquid water. That's why ice cubes float, even though they're colder than the water that they're in, and they're solid, but they float because they're less dense. And why do the water molecules go farther apart below 4 degrees C to 0? I don't know. It's something to do with stability, how they have to form the crystalline structure of the ice. Anyway, so floating ice acts as an insulating blanket over liquid water, allowing life to persist under the frozen surface. This is why bodies of water freeze from the top down, not from the bottom up. If ice did not float, ponds, lakes, and even the oceans would freeze solid. And you'd have all the things at the bottom living in them, but at the bottom be killed because for most living things, you freeze them, you kill them. It's just natural freezing. Of course, we have frozen human embryos, but they're treated special so they can be frozen and not killed. Okay, so and hydrogen bonds are forming and breaking all the time in any amount of water. And how do you make the water? The more hydrogen bonds they break, and when you reach 100 degrees C, water starts to boil, and water becomes a gas, and all these hydrogen bonds are broken, and the water molecules can escape into the air. Why ice floats. Okay, here's what I mentioned before about solvents in solutions. Solution is a liquid consisting of a homogeneous mixture of two or more substances. The dissolving agent is the solvent. The dissolved substance is the solute. You have one solvent, you can have many solutes. When water is a solvent, the result is an aqueous solution. And that's what most of your precious bodily fluids are, aqueous solutions. There's some oil-based liquids in your body, but mostly they're aqueous. Remember, water is the biological solvent. Explain why ice floats, because the atoms move farther apart between as they drop from 4 degrees to 0 degrees and become less dense. So water is actually most dense at 4 degrees C, less dense at 0 degrees C. And here's how water dissolves salt. Remember, sodium chloride break up into the ions when you put salt in water, and the water molecules surround these ions. And notice that around the chloride, it's the hydrogens of the water molecule there because they're positive, and this is negative. And then around the sodium ion, which is negative, positive, the red oxygen is pointing toward that surrounding it because that side of the water molecule is negative. Polarity of water molecules helps explain water's ability to support life, relationship to structure to function. The structure of the water molecule gives it that polarity, and that allows water to support life. Okay, chemical compound that releases hydrogen ion to a solution is an acid. A compound that accepts hydrogen ions and removes them from solution is a base. And hydrogen ions are really reactive substances. Every organism on Earth regulates how many hydrogen ions are dissolved in its body fluids. So chemists use a scale called the pH scale to measure how many hydrogen ions are in a solution, and also how many hydroxide ions. OH is hydroxide. And water can break into these two ions. As I mentioned before, oxygen likes to try to take away electrons from the atoms that it forms molecules with. And it tries to take it away from one of the hydrogens in the water. And occasionally it does. And then the water breaks apart. And a hydrogen ion goes one way, and the OH that's left from the broken water molecule goes a different way. And that's called hydroxide ion, and it has a negative charge. And a hydrogen ion has a positive charge. So this is constantly happening in your body, and you're constantly making acids and bases. And so And it's really important that we maintain what's called the pH level of your body fluids. Uh, and so we have things that are called buffers that minimize changes in pH, because even a tiny change in pH has really negative consequences to living things. So living things use buffers to minimize changes in pH. There's the pH scale right there. It's a scale of 0 to 14. It's a logarithmic scale. Don't worry, I'm not going to go into logs. But it means that there are, well, for example, neutral pH is pH 7. That's where the number of hydrogen ions in the solution equals the number of hydroxide ions in solution. If you get more and more hydrogen ions than hydroxide ions, that becomes a lower pH, and that's acidic. If you have fewer hydrogen ions than hydroxide ions, that becomes basic, and that goes up from 7 to 14. For example, since it's a logarithmic scale, at pH 6 has 10 times more hydrogen ions in it than pH 7. pH 5 has 100 times more hydrogen ions than 7. pH 4 has 1,000 times more hydrogen ions, and so on and so forth. In human blood, right around 7.4, and it better stay there. And then pure water is defined as having neutral pH, pH 7. Urine is usually a little bit acidic. Black-currant tomato juice, grapefruit juice, these are tangy, these are acidic. Lemon juice, stomach acid, battery acid. When you get really, really low pHs, those are actually really dangerous to living things. Even at pH 2, you spill some lemon juice on your skin, you're not going to feel any. Spill some battery acid on it, you're going to feel it. And same thing with the basic side, also called alkaline. Seawater, milk of magnesia, household ammonia, household bleach, oven cleaner. That's why when you clean the oven, you wear gloves, because it's dangerously basic. Okay, and so this is how acids and bases are defined. And every aqueous solution has a pH, because water breaks apart. But oils, for example, there's no such thing as pH for oils. Non-polar liquids. It doesn't make any sense. There's no such thing as pH for non-polar liquids. So basic, more hydroxide than hydrogen. Acidic, more hydrogen than hydroxide. Neutral, same amount of hydrogen as ion as hydroxide ion. And this has big effects in ecology. Carbon dioxide, when it combined with water, form an acid called carbonic acid, and it makes the seawater more acidic. So as you keep on raising carbon dioxide in the atmosphere, more of it's dissolving in the ocean, forming more carbonic acid and making the planet a little more acid. And this is one of the reasons why corals are dying all over the world, because the water is becoming more and more acid, because we're dumping more carbon dioxide into the atmosphere. So compared with a solution of pH 8, the same volume of solution of pH 5 has how many times more hydroxide ion? Remember, it's 10 times for every pH unit. So it's 3 pH units between 5 and 8. That's 1,000 times more hydrogen ions at 5. And the second solution at pH 5 would be considered an acid. At pH 8, it would be considered a base. So the release of CO2 from a factory in one region can cause ocean acidification that affects coral reefs. In another region, interactions within biological systems. Okay, so because radioactivity is an evolutionary clock, And so I get into a little bit of radiocarbon dating, but I'm going to use the next video to explain that. So I'm going to end this video here, and this is going to be used on Bio 106 Chem 3. So I'll see you later, and so the next video is going to be pretty short. All right, let me turn off the recording.